Explore humanity's megastructures, colossal projects, and bold visions, where cutting-edge engineering and smart technologies reshape construction, scale ambition, and redefine the future. The third Bosphorus Bridge, officially known as the Yavuz Sultan Selim Bridge, represents one of the most ambitious infrastructure projects in Turkey and a landmark achievement in modern bridge engineering. Constructed between March 2015 and March 2016 as a core component of the Northern Marmara Motorway project, the bridge was designed to connect the European and Asian sides of Istanbul while carrying both highway and railway traffic on a single deck level. Combining advanced engineering, large-scale marine operations, and innovative construction techniques, the project stands among the world's most remarkable hybrid bridges in terms of size, capacity, and aesthetics. Construction activities accelerated significantly in March 2015. One of the major milestones during this period was the rapid progress of the tower legs on the Asian side, which reached a height of 304 meters above sea level. These towers would later become the tallest bridge towers in the world at the time of completion. Simultaneously, the assembly of a massive derrick crane with a lifting capacity of 1,000 tons was successfully completed. This crane played a crucial role in handling extremely heavy steel components during deck installation and testing phases. Another major operation in March 2015 involved the transportation and installation of steel deck segments. The third steel deck section, weighing 940 tons and measuring 24 meters in length and 59 meters in width, was transported by a giant floating crane with a capacity of 800 tons. After being carefully lowered onto land, this deck segment underwent lifting tests using the 1,000-ton derrick crane to ensure structural integrity and lifting safety before final installation. Around the same time, the eighth steel deck segment, identical in weight and dimensions, was also successfully assembled, marking steady progress in deck fabrication and direction. In parallel with deck operations, the installation of inclined stay cables began. These cables form one of the two main load-bearing systems of the bridge, the other being the suspension cables. The initiation of stay cable installation marked the transformation of the project from foundation and tower works into a full-scale superstructure construction phase. Meanwhile, progress continued on the Northern Marmara Motorway, where reinforced concrete works on the European side E2 section reached 51% completion at the V17 piers. One of the most critical stages of the bridge project was the preparation for the installation of the main suspension cables. To enable this, the construction of the catwalks, known locally as kediolari, was completed. These temporary suspended walkways provided safe access for workers and equipment during cable spinning operations. Following the completion of the catwalks, saddle structures were installed on top of both towers, one on the European side and the other on the Asian side, allowing the main cables to pass smoothly over the towers. With all preparatory works completed, the spinning of the main cables began simultaneously from both shores of the Bosphorus. This operation required exceptional precision and coordination, as thousands of individual steel wires were pulled across the strait and assembled into massive cable bundles. Upon completion, a total of 645 kilometers of steel wire had been installed, forming the two main suspension cables that would carry the enormous loads of the bridge. After the cable spinning process was finalized, the main cables, initially hexagonal in shape, were compressed into a circular form. This compaction process increased structural efficiency and durability. The cables were compressed to a final diameter of 723 millimeters and securely fixed with steel bands. By this stage, the installation of inclined stay cables was also approaching completion. Approximately 500 kilometers of stay cable had already been pulled, demonstrating the immense scale of the project. As construction advanced toward the end of 2015, significant changes were introduced to improve efficiency. A new method was adopted for placing the steel deck segments. Instead of earlier lifting techniques, sliding cranes with a carrying capacity of up to 3,000 tons were introduced. These cranes lifted deck segments composed of two parts with a combined weight of 380 tons, enabling faster and safer installation. By this time, 42 steel deck segments had been fully installed and welded, leaving only 391 meters before the European and Asian sides would meet at the center span. By December 2015, the bridge structure had taken on its final form, and finishing works accelerated. In January 2016, the installation and welding of the 41st and 42nd steel deck segments were completed, bringing the total number of installed segments close to the final count of 59. Each segment was aligned with millimeter-level precision and permanently welded to ensure continuity and strength across the entire span. In March 2016, works continued following the completion of cable installation. The two main suspension cables, with a combined weight of approximately 13,000 tons, entered the final coating phase. This protective coating was essential to shield the cables from corrosion caused by wind, moisture, and the harsh marine environment of the Bosphorus. At the same time, the inclined stay cable installation reached the end of its first phase. Approximately 600 kilometers of cable had been installed, and 160 stay cables were fully mounted, stabilizing the deck and distributing loads effectively to the towers. The final phase of the project also included infrastructure and safety installations on the northern Marmara motorway. On the European side E2 section, pedestrian railings and vehicle safety barriers were installed at the V19 piers, ensuring compliance with international safety standards. These works marked the transition from heavy structural construction to operational readiness. By March 2016, the third Bosphorus Bridge had emerged as a masterpiece of professional engineering and advanced technology. Designed to carry 8 lanes of motorway traffic and 2 railway lines at the same level, the bridge set new standards in hybrid bridge design. Its elegant silhouette, combined with outstanding structural performance, positioned it among the most important bridges in the world. The successful completion of the project within a single year stands as a testament to meticulous planning, innovative construction methods, and the coordinated effort of thousands of engineers, technicians, and workers. Perched high above a rugged mountain highway, the construction of the Hilltop Restaurant stands as a remarkable example of modern engineering and human ingenuity. The road leading to this site winds dramatically up and down steep terrain, offering a breathtaking yet challenging route that highlights the marvel of highway construction in highland regions. Building safe and reliable access in such mountainous conditions requires innovative technology, precise planning, and constant supervision to manage risks such as soil erosion, rockfalls, and landslides. The project area lies at elevations ranging from 1,000 to 1,600 meters, where narrow carriageways, sharp curves, and steep slopes once made travel extremely hazardous. Extensive road improvement works were carried out to stabilize slopes, widen the roadway, and enhance alignment, ensuring smooth access for construction vehicles and future visitors. Advanced techniques such as mechanically stabilized earth walls, ground anchoring, and reinforced embankments were employed to overcome limited working space and unstable ground conditions. As a result, the Hilltop Restaurant now rises confidently above the highway, offering panoramic views and a safe resting point for travelers. This project not only transforms a dangerous mountain stretch into a functional landmark, but also contributes to regional connectivity, tourism growth, and long-term socioeconomic development of the surrounding area. After a devastating mudslide in northwest China's Qinghai province, a destroyed section of Provincial Highway 302 was rapidly restored using a temporary steel bridge. Heavy rainfall triggered the landslide in Kilian County, cutting off this vital transport artery and disrupting traffic to Sining City. Immediately after the disaster, local road authorities mobilized emergency teams, transported prefabricated steel bridge components to the site, and cleared thick layers of silt and debris. Within just 24 hours, the modular steel bridge was installed, precisely aligned, and connected to the existing roadway. By Friday evening, traffic was fully reopened, easing congestion, reducing travel time, and restoring normal transport. This rapid response ensured public safety and maintained economic and social stability in the region. This innovative road paving machine is designed to lay stone blocks in a remarkably short time. While manual paving allows a worker to cover only about 75 to 100 square meters per day, this machine can pave up to 300 square meters daily with significantly less physical effort. The machine is equipped with inclined conveyor belts on which workers place bricks and stones in a regular pattern. The conveyors automatically move each row forward until it is accurately positioned on the road's surface. Thanks to this system, Road preparation and stone laying are completed in a single continuous operation with a working width of 6 meters. The machine spans the entire roadway. After paving, workers fill the joints with sand. Stone roads are durable, attractive, and easy to maintain, and this technology helps revive their historical popularity. The assembly and installation of the roof at Al Wakra Stadium represent a major engineering achievement and a decisive milestone in the construction of this iconic sports venue. On April 26th, a critical phase of the project was successfully completed with the dejacking operation, marking the moment when the roof structure reached its final, self-supporting position. The roof, composed of an impressive 7,000 tons of steel, had initially been assembled at a lower level to ensure safety, precision, and efficient coordination. Once the full steel framework was completed, a carefully planned lifting process began. Using a synchronized system of hydraulic jacks, engineers gradually raised the massive structure in a controlled and perfectly balanced manner. Throughout the operation, continuous monitoring ensured that loads were evenly distributed and that the roof maintained the exact geometry required by the design. The dejacking phase was particularly delicate. During this stage, the temporary supports were progressively released, allowing the roof to transfer its weight onto the permanent structural elements. This required extreme accuracy, as even minimal deviations in angle or position could have affected the overall stability of the stadium. Thanks to meticulous planning, advanced engineering calculations, and close collaboration among all teams, the roof was fixed precisely at its final elevation and orientation. Completing this operation successfully was a remarkable feat, considering the scale, weight, and complexity of the steel structure. The accomplishment not only demonstrated outstanding technical expertise, but also confirmed the effectiveness of modern construction methods for large-span stadium roofs. With the roof now securely in place, Al Wakra Stadium moved one step closer to completion, showcasing innovation, precision, and excellence in contemporary stadium construction. The modernization of inland waterways in Europe is a crucial step toward improving efficiency, safety, and sustainability in waterborne transport. Among the critical operations within this project is the replacement of the gantry cranes, a task that exemplifies both engineering complexity and strategic planning. The Charleroi-Brussels Canal is an essential waterway for Belgium, providing a direct link between the industrial regions of Wallonia and the ports that connect to international trade routes. For decades, the canal's locks have been vital for ensuring smooth navigation and regulating water levels. However, the aging infrastructure at these locks has gradually become inadequate to meet the demands of modern shipping. The solution lies in comprehensive modernization, including the dismantling of outdated equipment and the installation of state-of-the-art systems. At the heart of the project, the gantry cranes, once the backbone of lock operations, were carefully dismantled. These cranes, which had served faithfully for decades, no longer met the requirements of modern navigation and safety standards. Removing them was not a straightforward task. The operation demanded precise coordination, as the cranes were massive structures firmly integrated into the lock system. Specialized lifting equipment and expert crews worked together to ensure that each element was safely disassembled and removed without disrupting other parts of the lock. The removal of the gantry cranes marked an important milestone, as it cleared the way for the installation of ultra-modern equipment designed to improve both efficiency and safety. The replacement was not merely a matter of switching old machinery for new, it involved rethinking the entire functional design of the locks. The new systems integrate advanced automation and monitoring technologies, enabling lock operations to be controlled with greater accuracy and reliability. This modernization ensures that the locks are fully capable of handling the increased traffic and larger vessels that characterize today's inland waterways. In parallel with the gantry replacement, BESIX and Frankie are carrying out highly complex civil engineering works to upgrade the pumping stations of the three locks. These pumping stations are critical for managing water levels and ensuring that vessels can move safely through the canal regardless of seasonal fluctuations. Modernizing them is as essential as updating the cranes, since both elements must function seamlessly together to guarantee the long-term reliability of the waterway. The project also represents a significant logistical challenge. Working on three separate lock sites simultaneously requires meticulous planning and coordination. Teams are deployed across Visville, Gosselies, and Marchiennes-au-Pont, each dealing with its own technical and environmental constraints. For instance, dismantling massive structures within confined lock chambers demands not only technical expertise, but also strict adherence to safety procedures. Every stage must be executed with precision, as the margin for error in such operations is minimal. Another noteworthy aspect of the project is its sustainability dimension. By modernizing the locks and replacing outdated equipment with more energy-efficient systems, the project contributes to reducing the environmental footprint of inland navigation. Improved pumping stations, optimized water usage, and automated control all help minimize energy consumption and emissions. This aligns with the broader European vision of promoting inland waterways as an environmentally friendly alternative to road transport. The replacement of the gantry cranes is thus emblematic of the larger goals of the Three Locks project. It demonstrates how careful engineering interventions can breathe new life into aging infrastructure, ensuring it continues to serve society's needs well into the future. The operation also showcases the expertise of BESIX and its partner Frankie, who combine technical skill with innovative solutions to meet the challenges of modern civil engineering. Ultimately, the modernization of the locks at Visville, Gosselies, and Marchiennes-au-Pont will enhance the competitiveness of the Charleroi-Brussels Canal as a transport corridor. Larger vessels will be able to pass through more efficiently, reducing transport times and costs. The time-lapse video captures the impressive construction process of the Three Locks project on the Charleroi-Brussels Canal in the Walloon region. Led by BESIX, the project focuses on modernizing three strategic lock sites located at Visville, Gosselies, and Marchiennes-au-Pont. These locks play a crucial role in inland waterway transport and have been part of the canal's infrastructure since the early 20th century. Much of it originally built by BESIX itself. Throughout the construction process, extensive earthworks, concrete operations, and structural upgrades are carried out with remarkable precision. The time-lapse highlights the careful sequencing of tasks, from excavation and foundation works to the installation of new lock structures and technical systems. Despite the scale and complexity of the works, river traffic disruption is kept to a minimum, allowing barge transport to continue as smoothly as possible. By the end of 2020, the 3 locks are equipped with ultra-modern, high-performance installations, entirely manufactured in Belgium. This major infrastructure upgrade significantly improves the efficiency, safety, and reliability of navigation on the southern section of the canal, supporting long-term economic and logistical development in Wallonia. Based on the Apollo Hawkeye Pederschab CAP 360 vertical vibration casting machine, the production of precast concrete box culverts is carried out through a fully controlled and sequential process using dry mix concrete and synchronized compaction. First, reinforcement cages are fabricated according to the required box culvert dimensions and structural design. Once completed, the cage is carefully placed onto a groove-forming pallet, ensuring correct alignment and cover. At the same time, lifting anchors and weep-hole formers are installed at predefined positions to meet handling and drainage requirements of the finished culvert. Next, the pallet is locked together with the outer jacket, forming a rigid mold assembly. This assembly is then positioned on the CAP 360 machine, where the inner core and outer mold work together to define the final geometry of the box culvert. After mold placement, dry mix zero slump concrete is transferred from the batching plant to the machine. Concrete feeding is performed by an XY feeder equipped with a belt distributor, specially configured for box culverts and U-drains. This system distributes the concrete evenly inside the mold cavity. During filling, synchronized VIHY core vibrators compact the concrete continuously, ensuring high density, uniform strength, and excellent surface finish. The filling level is monitored and adjusted using a laser-level system with PLC-based controls, which guarantees dimensional accuracy and consistent wall thickness. Once the mold is fully filled and compacted, tongue and groove profiles are formed by hydraulic pressing through the header, creating precise joint geometry for easy installation on site. After shaping is complete, the outer jacket is hydraulically pulled off the core together with the box culvert, maintaining the integrity of the fresh concrete. The mold jacket is then stripped from the box culvert using a crane, allowing the product to remain on the pallet. Immediately after demolding, a chemical curing compound is applied to the surface to reduce moisture loss. Finally, the box culvert undergoes initial curing by polythene covering, which protects the concrete and supports proper strength development before further handling or storage. This controlled process ensures consistent quality, high productivity, and durable precast box culverts ready for infrastructure applications. This presentation introduces Eurovia CS as a major infrastructure contractor operating across all regions of the Czech Republic and Slovakia. The company carries out complex road, highway, and transport projects, from surface repairs to full reconstructions. Key works include the overnight repair of the D1 motorway surface, reconstruction of the D2 concrete pavement over a 14-kilometer section, and major upgrades on routes such as R6 Lubanek-Bosov and Road 11405 at Preseka. Eurovia CS has completed thousands of meters of highways and bridges, placing hundreds of thousands of square meters of cement concrete pavement. Notable projects also include concrete paving at Václav Havel Airport in Prague under tight deadlines, modernization of tram junctions in Košice, and long-term road maintenance on Slovakia's R1 expressway. With millions of tons of asphalt produced, noise barriers, prefabricated elements, and drainage systems installed, Eurovia CS plays a key role in modernizing transport infrastructure. The Pohorka Tunnel project represents a major milestone in modern transportation infrastructure, designed to improve connectivity and safety along a key regional corridor. Located in a challenging geological setting, the tunnel extends for several kilometers through varying rock formations, requiring advanced engineering and precise planning. Construction began with detailed surveying and the installation of support systems to stabilize the terrain. Tunnel boring machines and traditional excavation methods were used in combination to efficiently remove material while maintaining structural integrity. Throughout the process, crews implemented continuous monitoring to manage ground movement, water infiltration, and air quality. Specialized teams also installed reinforced concrete linings, drainage systems, ventilation shafts, and lighting to ensure long-term durability and user comfort. The Pohorka Tunnel not only reduces travel time and eases congestion, but also enhances regional economic development by providing safer, more reliable transportation for drivers, commuters, and freight traffic. The V07 viaduct of the Kuzi-Marmara Motorway Port Connection Road is a landmark infrastructure project designed to strengthen logistics links between the highway network and the port area. Built to cross complex terrain with significant height differences, the viaduct plays a crucial role in ensuring smooth, safe, and uninterrupted traffic flow for heavy vehicles serving the port. The bridge has a total length of 875 meters, with a maximum pier height of 137 meters, making it one of the most technically demanding structures along the route. To achieve this, engineers adopted a reinforced concrete pre-stressed balanced cantilever method, a solution well suited for long spans and deep valleys where ground access is limited. Construction required approximately 50,000 cubic meters of concrete, reflecting the massive scale and structural strength of the viaduct. One of the most remarkable aspects of the project was the use of 12 form travelers operating simultaneously, allowing multiple segments of the bridge deck to be cast at the same time. This synchronized approach significantly increased efficiency while maintaining high standards of precision and safety. Each segment was carefully poured, pre-stressed, and balanced step by step, ensuring stability throughout the construction process. Despite its size and complexity, the entire viaduct was completed in just 1 year, demonstrating exceptional planning, coordination, and engineering expertise. Today, the V07 viaduct stands as a symbol of modern bridge construction, supporting regional development by providing a reliable and high-capacity connection between the port and the Kuzi-Marmara motorway. The reconstruction of the Stobart railway line over the M6 motorway was carried out through a carefully sequenced and tightly controlled construction process to ensure safety, precision, and minimal disruption to road traffic below. The work began with detailed site preparation, including surveying, setting out reference points, and installing temporary safety barriers and access platforms along the bridge structure. Protective systems were erected over the motorway to shield vehicles from falling debris during overhead operations. Once the site was secured, the existing track components on the bridge were dismantled. Rails were unclipped and cut into manageable sections before being lifted away using rail-mounted cranes. The old sleepers were then removed sequentially, exposing the bridge deck beneath. Ballast material was excavated and cleared from the structure, allowing inspectors to assess the condition of the bridge and prepare it for reconstruction. Following clearance, repairs and adjustments to the bridge deck were carried out where required. This included cleaning the surface, repairing damaged concrete sections, and ensuring correct drainage paths to prevent future water accumulation. After the deck was approved, new waterproofing layers were applied to protect the structure from moisture ingress and long-term deterioration. The next stage involved reinstating the track formation. Fresh ballast was delivered to the bridge using rail wagons and deposited in controlled layers. Mechanical tampers and regulators were used to spread and compact the ballast evenly, forming a stable base for the new sleepers. Precision was critical at this stage to achieve the correct track geometry and load distribution across the bridge. Precast concrete sleepers were then installed using specialized lifting equipment. Each sleeper was positioned accurately according to design spacing and alignment requirements. Once in place, the sleepers were checked for level and gauge before rails were delivered to the site. Continuous welded rails were lifted onto the sleepers, aligned carefully and secured using modern fastening systems to ensure stability and reduce vibration. After rail installation, welding operations were performed to create continuous rail joints, minimizing maintenance needs and improving ride quality. Welds were inspected and ground smooth to meet safety and performance standards. The track was then mechanically tamped to fine-tune alignment, level, and cant, ensuring the railway met operational tolerances. With the main track structure complete, final ballast profiling was carried out to support the sleepers and enhance drainage. Excess materials were removed, and the track shoulders were shaped to specification. Engineers then conducted detailed inspections, including geometry measurements and visual checks to confirm construction accuracy. The final phase involved dynamic testing and commissioning. Test trains were run over the reconstructed section at controlled speeds to verify structural performance, track stability, and ride comfort. Once all parameters were confirmed to meet regulatory requirements, the railway line was approved for full operational use, restoring safe and reliable rail traffic across the M6 motorway. The operation to lift the steel rebar cage for installation at Rubio Wash demonstrates careful planning and precise execution using a large crawler crane. Before lifting began, the reinforced steel cage was assembled on the ground according to engineered specifications, ensuring that all rebar spacers, ties, and alignment met structural requirements. Workers inspected the cage to confirm that its dimensions, shape, and connections were ready for placement into the trench. Once the assembly was complete, the crane positioned itself on stable ground near the excavation site. The crane operator and signal person established clear communication through radios and hand signals to coordinate every movement. Rigging crew members connected heavy-duty slings and tag lines to the rebar cage at predetermined lifting points. These connection points were chosen to maintain balance and prevent unwanted rotation during the lift. With the rigging double-checked for security, the crane began lifting the cage slowly. The operator raised the load just a few inches first to perform a trial lift, allowing the crew to verify that the cage remained stable and that the rigging held correctly. After confirmation, the cage was lifted higher and moved horizontally above the trench. Tag lines were used by workers on the ground to control any swaying, preventing collisions with nearby equipment or trench walls. As the cage hovered over the trench, the operator eased it into position with fine, controlled movements. Ground personnel guided the cage into the trench, ensuring it aligned precisely with the design location. Once seated correctly, the rigging was detached and the crane lowered its boom, completing the safe and effective rebar cage installation at Rubio Wash.